Okay, good afternoon, everyone. Um, Before we start, did anyone have any questions about assignment 5? Okay. If you want to send your ideas about assignment 5, you still have, a few hours, so that opportunity is still there. So if you want to do that, you can. Okay. So today I just want to kind of finish introducing the basics for rings. On Friday, I hope that we can learn about well, one of our main examples is going to be polynomial rings. So we want to learn about polynomial rings and the ideals of polynomial rings, things like that. Okay. Also, before we get started, I realized that I made a slight error when I defined integral domains. I forgot a piece of it. So let me just go back to that for briefly. Okay. So definition. Okay. An integral domain is just an integral domain is a commutative ring with 0 not equal to 1 in the ring. And this is what I forgot to mention. Okay. Because you can have a ring where 0 equals 1, and that's called a 0 ring. We're just saying, like, in an integral domain, 0 and 1 are going to be or have to be different. Okay, and then we still have the same condition such that there are no non-zero zero divisors. And I'll just rephrase that. That means that if AB equals 0 in R, then either A equals 0 or B equals 0. This is another way to phrase the statement that there are no non-zero zero divisors. We could just replace it by this phrase. Okay. And in the integral domain, in integral domains, we have the integers. We have things like the integers mod 5. We have the real numbers, for example. We have the polynomials with real coefficients, just as an example. And then like for non-integral domains, well, we saw that we have the integers mod 6 as an example. See, what's another example? You can look at the ring of polynomials can mod out by the ideal generated by x squared. We'll look at what that is, what it means to be like for an ideal to be generated by some element, but this is just to give you an example of a ring that is not an integral domain. Another example of a ring that is not an integral domain, well, you can just think of the Cartesian product of two copies of the integers as being a ring, where addition and multiplication is like coordinate wise. But in this ring, 0, 1 times 1, 0 is 0, 0. Just for example. Okay. Okay, so in Z cross Z, we can multiply two non-zero things and get something that's equal to 0, right? Which means it's not an integral domain. And Rx mod x squared, if you call x bar kind of the coset of x, then x bar squared is just equal to x squared bar, which is 0 bar. Okay, so if you take maybe yeah, okay, I'll come back. In the next page I'll come back to this example so we can see it in more detail. But just I want to also remind you that in Z mod 6Z we have 2 bar times 3 bar equals 0. Okay, so the coset of 2 times the coset of 3 equals 0, right? But 2 and 3 are neither of them are 0. So in lots of rings you can multiply non-zero things and get 0. And if you can't do that, that's special. That we call that an integral domain. So the integers are an integral domain. That's, I guess, the main, like, what reason, that's the reason you might call something integral. It's like the integers. The integers mod 5, that's an integral domain. Well, because any field is an integral domain, it turns out. Okay. Well, I just want to mention this example a little bit more. Okay, so let's talk about this example. I hope that it will allow us to talk a little bit more about ideals and so on. So first of all, our ring is going to be the ring of polynomials with real coefficients. So the elements of this ring are just polynomials in X, and all the A's are real numbers. And of course, n is greater than or equal to 0 in this definition. Okay, that's the ring of polynomials. And now I want to tell you, what is the ideal generated by x squared? Well, there's kind of two things we can describe it as. It's the set of all polynomials that look like x squared times f, where f of x is a polynomial with real coefficients. Okay, so if I take any polynomial and multiply it by x squared, well, I just get a polynomial that where kind of the lowest term starts with an x squared. Okay, so these are the set of polynomials that look like a0 x squared plus a1 x cubed all the way up to an x to the n plus 2, and then the a's are all real. Okay. And let's call this, well, let's give it a name. Let's call it I. Okay. And now we want to understand that R of x mod I is not an integral domain. So let's try and understand what are the elements of R of x mod I. Okay. Well, the elements are just elements of R of x, but cosets with I. Okay. So let's give this a name. Let's call it R, I guess, for ring. Okay. And let for f of x, a polynomial, let's just put a bar over it to mean the coset of f. Okay, so if you have any polynomial, when I put a bar over that polynomial, what I mean is an element of R, so meaning a coset of some polynomial, the coset of this ideal. So just as an example, if I write x squared plus 1 bar, that just means the coset of x squared plus 1. And that equals 1, the coset of 1. Why is that? Well, if I look at the difference of x squared plus 1 minus 1, that's an element of the ideal. Okay. So why is this part is true, since x squared plus 1 minus 1 is x squared, and x squared is an element of the ideal. Okay, and 1 plus I, that we could just call that 1 bar. Okay, so in R, x squared plus 1 equals 1. Okay. In fact, you can, like, things in R are not that complicated. In fact, if f of x equals a0 plus a1x plus a2x squared plus da 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 plus an times x to the n, then f of x bar is just equal to a0 bar plus a1, and that's it. Okay, so when I mod out by the ideal generated by x squared, I'm essentially saying that x squared is 0. Okay. And so that lets me say that all this stuff kind of goes away when I mod out by x squared. Okay. To see why f of x bar equals this, well, notice that f of x minus a0 minus a1x, that's just a2x squared plus an x to the n. This is a polynomial whose lowest term is an x squared. Okay, so this is an element of the ideal. Okay, so the elements of R are like not as complicated as the elements, like the set of all real polynomials. Like we can describe every polynomial, every element of R as like a0 plus a1 x bar, where a0 and a1 are real numbers. And then how do we multiply two things? Well, we multiply them just like we do regular polynomials, but then we mod out by x squared. So like a0 plus a1 x bar times b0 plus b1 x bar. Well, that's just a0 b0 plus a1 b0 plus b1 a0 times x bar, and then a1, then you also have an a1 x bar times b1 x bar, but x bar squared is 0 because x squared, like we're saying, when I mod out by the ideal generated by x squared, I'm saying that I'm kind of making x squared to be 0. Okay, so this is how you multiply two elements. So in particular, x bar times x bar is 0 in R. Okay. So now I have a ring which has a 0 divisor. It's actually like, not only is it a 0 divisor, like a power of it is 0. That's kind of, you know, a more restrictive condition than just being a 0 divisor. Okay. Okay. So one of the kind of, after making the correction about integral domains and a little bit of a review, I wanted to get back into, I wanted to try to talk about today some ring isomorphism theorems and talk a little bit about talk a little bit more about some of the other properties that rings have, like of ideals and all that. Okay. Okay. Okay, so if you remember, oh yeah, so let me go through some of the things we need, some of the notations we need to define. We need to know different types of ideals. Oh, this went really. Sorry, it's it doesn't want to focus for some reason. Okay, sorry about that. And I'll try and write something and then maybe it'll start focusing, or maybe you have to remove this. Okay, so some of the things we need to talk about: maximal ideals, prime ideals, principal ideals, I'm sorry, this is giving me. Okay, I hope that is better now. Okay, yeah, so we need to talk about maximal ideals, prime ideals, principal ideals. And I also want to talk about some of the isomorphism theorems. Okay, so yeah, the first isomorphism theorem. Okay, let phi from R to S be a ring homomorphism. Then there exists kind of unique phi tilde such that phi tilde goes from R mod the kernel of phi to phi of S or phi of R. And phi tilde is an isomorphism. And kind of, and I'll just draw a diagram for what phi tilde does. So you start from R, and then you mod out by the kernel of phi. Then you apply phi tilde to that. And then you view that as a subring of S. Okay. So what the first isomorphism theorem says is that to get from R to S by phi, first you reduce mod the kernel of phi, then you have this isomorphism phi tilde, and then you end up as a subset of S. Okay, and another way to think about it is that whenever you have a ring homomorphism, you get this isomorphism between R mod the kernel of phi and phi of R, and also no, let's just leave it there. you can actually say some more things like, well, I don't, yeah. Okay, anyways. This is the first isomorphism theorem. That means if you ever construct a homomorphism and you find out what the kernel is, you get an isomorphism, like an isomorphism, you get that for free. Okay. So you go to the trouble of proving that something is a homomorphism. You get some isomorphism coming from that. Okay. Okay. And there's one other, well, at least one other isomorphism theorem that I want to tell you about. And this tells you like correspondence. This is basically like there's a similar theorem in group theory. Okay. Theorem. Okay. Let I be an ideal of a ring R. Then there's a correspondence between ideals of R containing I and ideals of R mod I. Okay, and the correspondence is given by if I contains J and J is contained in R, you look at J bar, which is J mod I, which is just the cosets of I such as X is in J. Okay. So that allows you to take any ideal which contains I and turns it into an ideal of R mod I. So this is an ideal R mod I. And then if you have an ideal J bar contained in R mod I, you construct J by looking at all the X's such that X plus I is in J bar. Okay. And so, so if okay, that's the first part of the theorem. Let me tell you the second part. So it tells you, ideals which contain I correspond to ideals of R mod I. Okay. The second part of the theorem says that if I is contained in J is contained in R, and I and J are ideals, then you can look at R mod I, and then mod out by J mod I, and what you get is you get R mod J. Oh, I went too far down. Okay, and there's a similar theorem for groups. If you remember, all we're saying here is that you can cancel the denominators. Okay. Okay, let's now just take like 3-minute break. Then when we come back, we'll talk about maximal ideals, prime ideals, principal ideals. Yeah, so see you guys in three minutes.